Hello and good evening, or good afternoon, sorry. We shall be live in just a couple of minutes' time. This afternoon we're looking at organic chemistry practicals 5, 6 and 10, which is essentially the organic chemistry part of the course. If you're just signing in now, why not go along to the quick question site where we've got the live chat. Please do come in, see what's going on. You can download the sample work that we've got there. And also, if you could just check that my sound is working, okay, and we can get started in just a couple of minutes. Okay, good afternoon. Thank you for those who have come along to the room. Kay says that they can hear me okay, which is great news. Just to double check, hopefully you can hear me all right. And I'm loud and clear. It's Wednesday, it's the 17th of May, and today we're going to be looking at some of the organic chemistry practicals. Those are the required practicals 5, 6 and 10. If you've not seen us before, do come along and check out the website. We've got numerous resources throughout the A-level chemistry course. Our key revision content at the moment is on the push for the A2 course or the full A-level course, and we've got plenty of past revision webinars and plenty more to come ahead of the exams. So good afternoon. I'm just going to take you along and just show you where we're up to with our required practicals. So this is a OneNote file, and you can access that from the quick question section. Just follow the link there. You might need to just type that into a web browser. And we've looked so far at titration and enthalpy, which is 1 and 2, rates of reaction 3 and 7, E cell and pH, which are 8 and 9, and today we got 5, 6 and 10. So as we look here at the required practical content, we've got distillation of a product from a reaction. We've got tests for alcohol, aldehyde, alkene and carboxylic acid, and we've also got the preparation of an organic solid and test of its purity, and how to preparation of a pure organic liquid. All right, and that means we've covered all bar about 3 of the required practicals. If you just jump across to the organic 5, 6 and 10, we've got the key points here for these practicals. These again are accessible if you want to download them from the quick question webinar page. Feel free just to come along and download those as you need them. And just, if you've not got that, the link should be at the bottom of the YouTube page if you're there watching on YouTube. Just to show you where they all are, we're live here in the quick question section, which you can get to from the home page here. So we're on the required practical webinars. Takes us through to this page. You'll find links to the past webinars if you want to join the site. It'd be great to have you along. Here's our chat room, and you can also see here the OneNote resources and the practical questions, and as well as something from the specimen paper. The answers to all of these, as per usual, will go up on the past webinar section, which is part of the members part of the site. And I think we're going in here. There we go. Required practicals 5, 6, and 10. I'll upload those at the end of today's session. Great. Okay, let's just move that screen out of the way and let's have a look at the key points. So practicals 5, 6, and 10. Hopefully you met 5 and 6 back there in your first year of the course. And that is how to essentially distill a product. So here we go. Number 5 is distillation of a product from a reaction. The key one that you probably will have done is you will have made, you would have reacted alcohols, and you would have gone from alcohols to either aldehydes, and then from the aldehyde you might have made a carboxylic acid, or you might have gone to form a ketone, and you'd have probably done tests for those. Equally, if you'd not done that, you might have made gone from cyclohexene to make cyclohexanol. Either way, you should have come across some apparatus that looked like this, where we're doing a distillation reaction. And I've got 2 setups here which I wanted to show you today. We've got distillation of a product. The first on the left-hand side, which is almost distinctly the same as that on the right-hand side, except that it's got an extra sort of section above it. So we've got a round bottom flask here where we've got a mixture. Now, just to point out, in this mixture we often have some anti-bumping granules, which we add in, and those are added in to reduce the boiling effect, to stop it being such a vigorous boiling effect, and stops it boiling over. Then we've got on top of this a fractionating column, and the purpose of the fractionating column there is to separate out the liquids, and essentially giving yourself a bit more room in which to do the separation. Then as we go up, we have a thermometer. The thermometer is there for obvious reasons. We've got the thermometer to measure the temperature, and the thermometer will hold at the boiling point of the liquid. So if we had here a mixture of, let's say, ethanol and maybe water, the initial heating we would heat up to, I think off the top of my head, I'm not sure for certain, it's about 78 degrees Celsius. Importantly, is the boiling point of ethanol. If we were trying to separate these 2 mixtures, we'd heat to 78 degrees Celsius, the boiling point of ethanol, and then we would condense out, and we would get condensing, because here we're going to get, and this is, if we want the complete name, it's a Liebig condenser. We have water in, and we get here water out at the bottom. And the reason we do that, that is going to cool the gases to below their boiling point, and they will then condense out. So we end up collecting a purified liquid. The other way you may have seen it is without the fractionating column. So if we do a distillation, as we see on the right-hand side, you notice that there's not the addition here of the fractionating column, but there's quite a long tube essentially to the round bottom flask. What we're going to get here is something which isn't quite as pure a product out at the end. But here we got the description of how we might use the distillation here. In this case, rather than for separating ethanol and water, here we're actually going through the process of reacting an alkene, in this case a cyclohexene, which looks like that, the double bond in, to form a cyclohexanol. The thing about this particular reaction is, because we've not got this large fractionating column here, we get an impure product out at the end. Because we've got an impure product, we need to come up with further ways of purifying that liquid. Now, we'll go through and see the ways of purifying that liquid when we go and look at practical 10 and think about that a little bit further. So they're the two ways of distillation of a product. The other way, and I'm going to include this really because they often ask about reflux and distillation. Although the required practical is for distillation, there's no reason why you wouldn't know about reflux at the same time. And reflux is exactly the same sort of thing as distillation, apart from rather than having the reflux condenser horizontal to your reaction mixture, you have it vertical, so it's going straight up. And what this allows for is for the continuous heating of a substance, because what's going to happen here is whatever it is that you're reacting, you're going to heat up, it's going to rise its way up this tube as you heat it up, and then it's going to cool as it gets to the cooling jacket, and it will condense and drip back down. As it drips back down, it will react with the mixture at the bottom and start to condense back up the tube, and then it will boil, it will evaporate up the tube, and then it will recondense and come back down. So we end up with this refluxing situation where we're getting gases which are evaporating and condensing, evaporating, condensing. Now, this is important partly because of sort of the required practical 6 where we need to identify our alcohols, but it's also because, well, it's because we need to identify our alcohols partly. You will come across this because if you look at primary alcohols, I'm not going to go into detail about what primary alcohols are. We can oxidize these to form aldehydes. And these can then go on and form carboxylic acids. I'm just going to display that like this, and we will check in a minute how we identify both of these. And what we use here is K2Cr2O7 in acid, and this is acidified potassium dichromate. And heat. The key here is to get the aldehyde. We have to do distillation, because that allows for the product to be tapped off before further oxidation occurs. But if we allow for reflux, then we continue reacting these substances together and we get further oxidation from the carboxylic acid. The secondary alcohols, hopefully you're aware. If you're not, this is good revision. Will go and they will react with a ketone or to form a ketone, and they will not go on and react to form a carboxylic acid. And our tertiary alcohols do not undergo any oxidation whatsoever. The secondary alcohols, again, are also using potassium dichromate and acidified potassium dichromate. So there is how we do distillation, and also the indication here of how we do reflux. And that really leads on to the required practical number 6, which is how to test for some of these things. So our tests for alcohol, we've essentially already said here. We've got our acidified potassium dichromate, Cr2O7, we call H+. Notice the color here is orange. Okay, and in reaction, if it acidifies the alcohol, it will turn green. This gives us a test tube reaction for identifying an alcohol, where acidified potassium dichromate will be reduce the chromium from dichromate to Cr3+, which is green. Okay, so there's our test for alcohols. The aldehydes, so here, this is if we were going from a primary alcohol, and we oxidize to form the aldehyde using acidified potassium dichromate, and we did this by distillation, we would hopefully here form the aldehyde. And then we've got two tests. We've got the tollens reagent, which you need to be aware of, AgNH3 square brackets plus, which goes forward to form, and essentially we get the reduction of the Ag plus an electron to form our silver mirror. That is importantly here, I'll just point that out, in the presence of an aldehyde. So these are both tests for aldehyde. Let me just heard the pop go up. You do need to know how to make up the silver nitrate solution for AQA. That's one of the requirements that they ask us to do. So I'm just trying to remember. Certainly, that's something that's going to come up in your paper 3. It could come up, but potentially it could also come up here in your paper 2. All right, so it's a practical test, so I would expect to see it there in your paper 3, if it's going to come up anyway. The next one here is your failing solution. A failing solution goes from that lovely blue to the brick red, again in the presence of an aldehyde. You don't need to know how to make the failing solution, but know that these are both positive tests for the presence of the aldehyde. Okay, moving on. The one that's not on here, which I've forgotten to add to my notes, is the reaction of an alkene. And this is the addition of bromine water. Okay, and you see here an orange to colorless reaction in the presence of an alkene. Now, the thing to note here as well is this, if you use an excess, just be aware that excess bromine water, here you would end up with a orange solution, because it would react with all of the alkene and then leave you an orange solution left over. So you've got to ensure that you're using only a small amount of the bromine water. If you use too much, you may well observe still an orange solution because you've reacted with all of the alkene. That could be a way of improving an experiment, for example. The final test here then is your carboxylic acid. Carboxylic acid we test as an acid, and so to be aware, a test tube reaction. Okay, 9727. I'll come back to the tollens reagent. I'll just finish off here the carboxylic acid, and we'll pick up the tollens reagent for you. Don't worry. The carboxylic acid there is the sodium carbonate, or well, in fact any carbonate, but often used is sodium carbonate. That's often as a solution, and the description that you're going to use is you're going to be describing as either bubbles. I tend to use bubbles because I always struggle to spell this word, where we got effervescence. Vescence forming then. Okay. So, and then back to just to identify there for sure the question about how do we make the tollens reagent. That's a funny emoji. I've not seen that one before. I'll do this in black. So preparation of the tollens reagent. Here, what you're going to make sure you do here is you are going to be adding ammonia solution to silver nitrate, so AgNO3 AQ plus ammonia, and ammonia solution, and that is going to form your ammonium silver compound, and you add just enough to form a colorless solution. Okay, and then once you've done that, you simply going to add that there along in alkaline conditions to your expected aldehyde. Evening or afternoon 0431. So there you're forming a silver nitrate and ammonia just enough to form a colorless solution, then warm with OH minus and your expected aldehyde, or your sample really, isn't it? You're going to do that quite carefully. Cool. No worries. So there's our required practical 6. Make sure you know all of those tests. So carboxylic acids, alkene, failing solution, and tollens reagent. quite likely they'd ask you to come up with a way of identifying perhaps between some different samples, perhaps between some different types of alcohols, and you've got to be able to come up with a way of doing that. And we'll see some examples in a minute. Finally, then, practical number 10, which is from the year 2 course. Yes, you can use your carbonate there. Okay. The practical 10, you may well have seen this. You might have done something like making aspirin. Making aspirin here. Key things that you probably will have done in that process is you probably will have done a distillation. All right, and you probably will have done a reflux. So those essentially they're synoptic in the sense that you should be able to recall how you do the distillation, how you do the reflux that we've just seen from our required practical 5. I'm not going to go through those again. If we pull up actually what the key that they've got here for number 10 is how we then do the preparation of a pure organic solid and test of its purity, and the pure organic liquid. Okay, the question there, 9727, you don't need to know the specific chemicals needed to make aspirin. However, in terms of context of the question, there's no reason why they couldn't ask you about aspirin, because when you're doing that reaction, you're talking about a nucleophilic addition elimination reaction. So they could give you perhaps a reactant that they're talking about that you might make them, and then they'd be expecting you to potentially give mechanisms for the reaction and suggest a way of actually perhaps undertaking the actual practical chemistry. The key here then is that we've got separation of some different sorts of substances. I'll look here briefly at separating liquids to start off with. So if you want to separate liquids, we've got a few simple ways of doing. Initially, we've got washing. All right, so washing here will remove impurities depending on their solubility. Okay, so if you've got water-soluble impurities, washing with water, mixing with water will react those things together. That would dissolve the water-soluble impurities, and then you could put them in something here like a separating funnel. Okay, all the separating funnel does is it allows any immiscible substances, oh, there we go, it's gone, to separate. So you end up with 2 separate samples, and then you can simply tap off each sample. Now, the thing about that is you may end up with an aqueous layer, like it's saying here. You might have mixed your liquids together, and therefore you can tap that off, and you've then still got an impure product which might have a certain amount of watery substance in there. In that case, you can add things like drying agents, so calcium chloride and magnesium sulfate, and these will absorb from that substance excess liquids. Once you've got a impure product, immiscible, yeah, sorry, 9728, immiscible. Miscible is a fancy word for do not mix. Okay, miscible means mix. Immiscible means do not mix. So these 2 layers that we're seeing here are immiscible. Once you've got your impure product, then you could then push that back, and you could do some distillation that we've seen before to purify your liquid in that way. Cool. The second process then, so that's if you're trying to separate 2 liquids. If we've got some products, now I don't think, oh, there we go. So there's our distillation process highlighted again if we've got 2 liquids. Once we've got our 2 impure liquids, and we might include a fractionating column. Yeah, could you use a button 0431? Thanks a lot for that. You can a Buchner funnel, and I've not drawn that yet. A Buchner funnel is absolutely correct. We're going to add that in. And this, remember here, we were talking about separation of two liquids. If we're now talking about a solid from liquids, and that is certainly the case that we had with, let's say, your aspirin making. Be aware of a Buchner funnel where you filter and be able to draw it. Certainly, if I were you, is where you and I'm really bad at drawing these, but this would be good enough to get me the mark. A key thing about your Buchner funnel here, and you put your sample in the top, okay, is that you are filtering under reduced pressure. Excuse me just a second. Okay, and I'll just draw your products at the top. You would end up with your products here in red, staying behind in your filter paper. Yep, just be aware that when you're using the Buchner funnel that you wet the filter paper first, and that just to stop any product passing through. It basically sticks it to the top of the surface. Okay, remember here that you are going to some sort of pump to reduce the pressure. Okay. The key about the Buchner funnel is that you're going to end up with impure solids here, and we need to be aware of how we purify impure solids and how we can then measure their purity. So the impure solids we can purify by doing recrystallization. There's two L's there. Cool. So the thing about this is you're going to use a hot solvent, okay? And the other thing is you want your substance to be soluble in the hot solvent, and you want it to be fairly or close to insoluble in the cold solvent. What that means is that in the hot solvent, if you completely dissolve the substance in the hot solvent, what that means is you will have impurities can be filtered out. And then in the leftovers, then as you recrystallize here, the pure product can be refiltered, can be filtered with our Buchner funnel before. I'm not going to go through the processes here because I think they're quite, quite self-explanatory. But do ask if you've got any questions there about the recrystallization. Moving on then to the final part then is testing the purity. And this really is for a solid sample. Again, because obviously you can't do a melting point, just be aware of a liquid because it's already a liquid. That really doesn't make sense. But what you're going to have here is you've got some sort of way of heating the sample. Yes, that's correct, 727. Here we've got a way of heating the sample, and the idea here is that we can heat slowly, all right, or we've got control over the heating. So when we're doing this, we're going to heat quickly to below the melting point, and then we will reduce the heating rate as you get close to the melting point. The reason for that is if you start heating too quickly, you could otherwise you're going to go past the melting point. If you're ramping up the temperature very quickly, basically your heating block isn't going to have time to slow down, and it would heat past your melting point, and you're not going to notice exactly the temperature it melts at. Pure products have a sharp, that's going to be sort of plus or minus 2 degrees Celsius melting point, and that's also going to be close to a data book value. The reason that you end up with a broad range of melting points is because you end up there with a sample which has got different intermolecular forces, and you get different intermolecular forces depending on whether or not you've got ionic substances dissolved in there, or you've got substances perhaps with more hydrogen bonding, or you've got larger substances, which just mean things can't get as close together. And as you start to heat up, all of these things start to rearrange and will affect the overall melting point, either making it stronger, but generally and more often making it lower than normal, because it's adding a certain amount of irregularity into the structure, often enforcing that the intermolecular forces are further apart. If they're further apart, they're longer, and therefore if they're longer, they're a weaker intermolecular force, and therefore a lower melting point. Okay, so I think that covers the key points there for the practicals 5, 6, and 10. And those, like I say, are the key points from the practical course that you've done. Most likely to come up in the paper 3, but don't be surprised if you get asked those sorts of questions bedded in across your paper 2 as well. They're not going to appear in your paper 1 because your paper 1 is, of course, your inorganic chemistry. All right. Okay. I don't think I really understand that comment. Anyway, let's have a quick look and see a couple of questions. It's 4:30 now. (9727) practice questions for practical skills. I would do as many of these examples as possible. Make sure you know the practical inside out, and be aware, think practically how you do things. Think about how you've done them in exams. So here we'll just have a look at a couple of these. Now these are from past exam questions. They don't include the sort of extended response answers, and I will do a session on the extended response answers in the coming weeks to think about, but they do at least deal with things like how to answer practical style questions. Here we go, and this is a classic thing, is make sure that you can draw labeled diagrams of your apparatus. In this question, they're asking for refluxing, but make sure you can also draw them for distillation. Make sure you can draw them for things like Buchner, funnel, and filtration. These are common things that they expect you to be able to draw and be able to explain as well why they work. All right, so they're a classic sort of question. I'm not going to draw the label diagram because, well, A, it's in the answers, and B, we have looked at that just a few minutes ago. I just want to talk through some of the key points. Just give this a second to anti-bumping granules. Why do we add these? And we've talked about that already, and we're talking about particularly when refluxing. The real reason behind it is if you have a reflux in there, you don't have bumping granules. What happens is you end up with large bubbles which overboil. Bubbles occur at what are called nucleation sites, and by adding the anti-bumping granules in, you add lots of nucleation sites. So this actually makes smaller bubbles That just looks like a person now, so I'll add in some more bubbles. Create smaller bubbles and importantly stops the overboiling. Then here we got draw the structure of a different organic product form when the acidified potassium dichromate is not in excess. So in other words here, presumably here, knowing our idea of primary, secondary, tertiary alcohols and the sorts of products that can be formed when we do oxidation. So the fact that we can get aldehydes, the fact that we can go on to form carboxylic acids, and the fact that these only go on to form ketones. Okay, here we've got a nice question. Question 2. I don't want to go through this particularly because I think it's a really good test for yourself. But here, following parts of compounds can be distinguished by simple test tube reactions. So there, test tube reactions. Can you come up with ways? Sorry, I'm meant to come here. Key points. Can we use our knowledge of test tube reactions that we've got on this page to design some sort of practical? Here we are. So butane 2-ol and 2-methyl propan 2-ol. Okay, observations with both. Here we go. Propane and propene, hopefully quite an easy one. Silver nitrate and sodium. Now this one here, just to be aware, that's actually testing for, essentially is testing there for the presence silver ions, and you do that with a chloride, bromide, or iodide. So that one there is not really an organic practical question, but it's certainly a good practical question that they could ask in the paper 3. And again here, magnesium barium question. This is about your group 2 hydroxides versus sulfates. So it's not really a question about organic, but again, a paper 3 question for sure. Here we go, a lovely picture of some distillation apparatus. The question concerns the oxidation of a primary alcohol, suggesting reagents. Okay. We've got already our acidified potassium dichromate at the top, so this is presumably alcohol down the bottom. Let's take the chemical change that causes the solution in the flask to appear green. Okay, so again, knowing what's going on in the reaction. Here's a practical question. Water baths over Bunsen burners. I mean, that's a really good question. That's a safety question at the end of the day, because you don't want to overheat. But importantly, if you don't want to use a naked flame when you've got flammable substances. So be aware there, heating mantles are a safe way, or water baths are a safe way of heating. Suggested reagent that could be used to confirm the presence of an aldehyde in the distillate. Again, test tube reactions. Sample of 2-methyl propanol was contaminated with butane 2-ol. Okay, so primary versus secondary versus tertiary alcohols again. So draw the structure of tartaric acid. So there's a question on your chemistry knowledge. Again, question. Again, here we go. Testing our understanding of observations. And again here, tartaric acid, a test tube reaction here, thinking about our carbonate reactions. Suggests why the test cannot distinguish between primary and secondary alcohols. Presumably that's something to do with they'd both turn acidified potassium dichromate green. Baking powder usually contains starch. Starch is added to absorb any water vapor that may come into contact with the baking powder when the container is opened. Deduce a reason why this water vapor needs to be absorbed. Okay, so again, a practical question there, which is really getting you to think about the sort of chemistry that's going to be occurring, and what you've got to do there is it's not necessarily going to be a clear and obvious answer, but it just requires you just to do some sort of thinking. Okay, here you're thinking about a baking process. Okay, and so you're talking about breads and cakes. The thing here is you've got something that's solid, and you've also got tartaric acid, which is solid. So if you're actually mixing the two together with some sort of water there, um, you would start a reaction before your sort of baking process. So that's the sort of thing they're trying to get you to identify, that you realize something's a solid or a liquid. Okay. Here, okay, again, purpose of anti-bumping granules. Um, a drawing of distillation apparatus, being able to look at some sort of information as well about the process. We'll have a look and see if there's one more to do. 0149, any carbonate would do. Sodium carbonate, both of those would be absolutely fine. Again, testing between primary, secondary, tertiary alcohols, you sort of get a little bit bored of the response after a little while. You sort of end up repeating yourself. But again, don't be complacent, I guess, is something to be aware of. Do read the question. If it make sure, and certainly when it comes to looking at some of the specimen papers later on, the paper threes, make sure you do carefully answer the question, because when we look at the 6-mark questions in a couple of weeks' time, maybe probably half-term week, just really be careful that you're being specific with your answer, because if you start sort of answering stuff that isn't within the question, then you're really wasting your time within the exam. Hey Shay, some of these are past ISA paper questions and some of them are from past exam paper questions. Importantly, they are all out of AQA exam stars. There is here on the sheets, this is from the specimen paper. I'd encourage you to have a look at this one. Indeed, perhaps go away and have a look at. We'll talk about the marking, like I say, another time. This is a 6-mark question from a practical paper, and this is what I'm saying about. Yes, we read this question. It's about recrystallization. So this is like the year 2 sort of stuff. It says we're not required to describe the full procedure. So that means there's very little marks going to be available for discussing actually the crystallization. What it wants us to do is to identify how we'd get suitable solvents to do the recrystallization. All right, that's a really good question actually to have a look at. If you want to have a look at that, it's on the site. We've been through here the required practicals 5, 6, and 10 in quite a lot of detail. Where am I going? That's it. What I'd encourage you to do, so if you've not done so yet, is just pop along to the quick questions section. If you want to pick out these past paper questions, you can find them here. Drop me a line if you've got any questions about them. We're going to stop the webinar in just a moment. I'm going to put up in just a moment, just as I knock offline here, is I will put the answers in the required practical section 5, 6, and 10. All of those will be available, of course, to all of our full-time subscribers. If you like the video content, please do share both the site and the YouTube videos with your colleagues. I'm just going to check to see if we've got any questions here just before we go. Shay, it's a pleasure. I hope you guys have found the session helpful. Just to be aware, next week we will be at a slightly different time. I'm not around at 4 o'clock next Wednesday. Just keep your eyes open. I'm probably change it to the Tuesday at 4 o'clock, but I will update that information on the website and also let you know through the webinars. Great, thanks 0149. just be aware, tomorrow evening, 8:30 p.m., we're going to be looking at period 3 oxides. So tomorrow night we'll be going through period 3 oxides. If you want to come along, join the site, come and see what we're doing. So we're doing period 3 oxide, or period 3 oxides and elements. That's going to be at 8:30 p.m. We'll be live on the website in the live webinar room. Really hopeful, sorry, it's been a long day. Really pleased you find the sessions useful. And like I say, if you've got any questions, you can always ask me in the chat, drop me an email, and best of luck with all of the revision. I'll say goodbye for now and have a good rest of the day.